Okay, so when we last left off, we discussed writing net ionic equations and predicting reactions such as precipitation reactions. In today's class session, we're going to focus on a superclass of chemical reaction known as redox reactions. So what is a redox reaction? Well, it's a transfer of electron between atoms or molecules. So it results in a change of the oxidation state of the reactants compared to the products. So we've actually already seen redox reactions at play. So for example, if we have lead solid reacting with oxygen gas, that in turn gives us lead oxide. Now, if we look at the charges of lead and oxygen, lead and oxygen both have a 0 charge in our reactant. In lead 4 oxide, lead now has a +4 charge and oxygen has a -2 charge. So we clearly see that there's a change in the number of electrons or the charge of each of our atoms before and after this redox reaction. Okay, so what is the formal definition of oxidation state? It's the charge that a single atom would have if all the shared electrons are in covalent bonds are assigned to the most electronegative atom. If you need a refresher on electronegativity, here's the table below. Essentially, fluorine is the most electronegative, and atoms have decreasing electronegativity, moving away from fluorine, moving down a column and to the left across a row, electronegativity drops. Okay, so to calculate oxidation state and oxidation number, I like to think of it as the hypothetical charge of an atom, assuming all bonds between atoms were treated as ionic bonds. Now, the reason why I like this definition is that it allows us to calculate oxidation number. We can use the methods that we use to calculate the charge of a cation in an ionic compound. So the first method is you can just cross the subscript of each atom into the oxidation number of the opposite atom. So to give you an example of this, so HCl, if we reverse cross our subscripts, that gives us an oxidation number of +1 for hydrogen, and chloride has an oxidation number of -1. Likewise, by analogy, in the ionic compound sodium iodide, if we reverse cross our subscripts, that gives us sodium plus and iodide minus. And so that gives us both the charge and the oxidation number. Okay, so let's look at this next example. So for copper 3 iodide, what would you expect the oxidation number of copper and iodine to be? What's the oxidation number of copper using this method? And don't be shy to share your responses in the chat. What is the oxidation number of copper? +3, yep. And iodide has an oxidation number of -1. Likewise, in nitrogen trifluoride, what is the oxidation number of nitrogen? What is the oxidation number of nitrogen? And what is the oxidation number of fluorine, following similar logic? What would the oxidation number of nitrogen be using this method? What would the oxidation number of nitrogen be following this method? Yep, 3+, yep, or +3. Fluorine has an oxidation number of -1. Essentially what we're doing in this theoretical charge method is we're treating our covalent compound as if it's ionic, and then in turn, we're solving for the theoretical charge or the oxidation number of our least electronegative atom, similar to how we solved for the charge of a cation. Let's look at another example. Lead 4 oxide, so we have PbO2. So if we reverse cross our charges this time, that gives us lead +2 and O -1. Now, oxygen typically has a charge and oxidation number of -2. So we need to multiply both of our oxidation numbers and both of our charges by 2. That gives us lead +4 and O2-, and now we're matching the literature and common charge preferences and oxidation number preferences for oxygen. So looking at carbon dioxide, let's take about a minute, and I'd like you to propose the oxidation number of carbon and oxygen in carbon dioxide. What would the oxidation number of carbon be in carbon dioxide? Remembering that we need to adjust our oxidation numbers to match the common preferred oxidation number for each of our atoms.
+4.
+4, exactly right. So just to showcase the logic behind that, we reverse cross our charges. That gives us carbon +2, oxygen -1. Oxygen prefers an oxidation number of -2. So we multiply both of our oxidation numbers by 2. That gives us carbon +4 and oxygen -2. Perfect, perfect. Now, the other method that we can use is similar to calculating the charge of a transition metal. We can solve for the oxidation number of the least electronegative atom. So for example, the oxidation number of our cation is equal to the charge of our anion times the number of our anion minus the total charge over the number of cation. This formula is using this idea that the total charge is the sum of oxidation numbers. So to showcase how we apply this formula to a ionic compound, so we'd say the oxidation number of aluminum, or the theoretical charge of aluminum, is equal to the charge of our anion, which is hydroxide, OH-. We have 4 of our anion at play. Our total charge is -1, and we have 1 aluminum cation. So that in turn and there should be a -1 next to this. And that in turn gives us an oxidation number of aluminum of +3. Set it up like this. For sulfate, let's try to calculate the oxidation number of sulfur and sulfate. Well, looking at our anion, in this case it's O2-, so we have -2. We have 4 oxygen atoms. Our total charge is -2, and we have 1 sulfur atom. So if we take the absolute value to calculate the oxidation number of our cation, which is going to be positive, that in turn gives us an oxidation number of +6. Does this make sense to everyone so far? The equations are exactly identical to the equations we discussed all the way back in chapter 3. Any questions on this idea so far? If not, let's continue on and let's now discuss some rules for assigning oxidation numbers. And these are rules specific to this chapter. So the oxidation number of all atoms will add up to the total charge of the molecule or ion. Okay? Free elements always have an oxidation number of 0. So for example, if you see calcium solid just in its normal, just written with no charge, this has an oxidation number of 0. The preferred oxidation number of a main group metal is equal to the group number. So for example, if you have lithium, so lithium solid currently, it has an oxidation number of 0 as it's a pure neutral element. Lithium solid would overwhelmingly want to react to generate lithium plus. So we notice that lithium is a 1A metal, so it prefers to have an oxidation number of +1. So this +1 is the preferred oxidation number. Just like in our example when we discussed charge preferences and the preferred charge of a metal. Now, there's a wonderful shortcut for metals in that the oxidation state is equal to the metal charge. So for example, calcium 2+ aqueous would have an oxidation number of +2. By the same token, if we had, for example, whoops, that's not the right color, one moment. For example, if we have titanium 4+, what is the oxidation number of titanium? What is the oxidation number of titanium? Yep, +4. Perfect. So continuing on with this idea, for monoatomic ions, the oxidation number is equal to the charge of the common ion. So for example, for most cations, we know like the charge is equal to the group number. And we know for most anions, the charge is equal to the group number -8. So we've already seen, for example, that lithium solid likes to generate lithium plus because lithium is a 1A element. Likewise, chlorine likes to generate chloride. And as we can clearly see, chlorine is a 7A element and it likes to adopt a -1 oxidation number. So this is the preferred oxidation number. If, for example, you see an ion just naturally written in the chemical equation, for example, S2- aqueous, we can clearly assign its oxidation number as -2. Okay, so oxidation number preferences are pretty close to the charge rule preferences that we discussed earlier. Okay, so let's look at polyatomic ions. The sum of all oxidation numbers are equal to the charge of our ion. So thinking about just natural oxidation number preferences, oxygen prefers to adopt a -2 oxidation number. Hydrogen prefers to adopt a +1 oxidation number. So then, if we add them together, the total charge, which is equal to -1, is equal to the oxidation number of oxygen times the number of oxygen atoms plus the oxidation number of hydrogen times the number of hydrogen atoms. And we see that the total charge is equal to the sum of oxidation numbers. Does this make sense so far? Does everyone understand where I got the -2 and +1 assignment from? we're using our oxidation number preferences, which mirror our charge preferences. Okay, so let's look now at neutral molecules. So neutral molecules, the sum of all oxidation numbers are going to be equal to 0. So for example, H2O. So if we look at water, so we notice very clearly that hydrogen will have a +1 charge, oxygen will have a -2 charge, and as such, hydrogen will prefer to adopt a +1 oxidation number, oxygen a -2 oxidation number. So we know that the total charge, which is equal to 0, is equal to the oxidation number of oxygen times the number of oxygen atoms, plus the oxidation number of hydrogen times the number of hydrogen atoms. And we see that this relationship does hold true. The total charge is equal to the sum of oxidation numbers. Does that make sense to everyone? Any questions on this idea? A free element is referring to the neutral species. A monoatomic ion is referring to a charged species. Does that make sense? So one is neutral, the other is charged, and as a result, they have different oxidation numbers because they have a different total number of electrons. For example, chlorine is the pure element, while chloride is the monoatomic ion. They have different numbers of electrons, they have different total charges, and they have different oxidation numbers. Perfect, perfect. So let's keep going now, and let's talk about some unique cases which make sense if you think about electronegativity rules. So the oxidation number of hydrogen is +1 in covalent compounds with non-metals. Essentially, we have a more electronegative atom. Okay, so for example, in this case, hydrogen has an oxidation number of +1. And as a result, carbon has an oxidation number of -4. In hydrochloric acid, hydrogen has an oxidation number of +1. Chlorine has an oxidation number of -1. In ammonia, hydrogen has an oxidation number of +1. And what about nitrogen? What would the oxidation number of nitrogen be if nitrogen is the more electronegative element? If nitrogen is the more electronegative element, which means it will have most of the electron density, what is the oxidation number of nitrogen? -3, exactly right. Perfect, perfect. Now looking at sulfuric acid, hydrogen's oxidation number is +1. Oxygen's oxidation number is overwhelmingly -2. So we can solve for the oxidation number of sulfur. And the way that we do that is we take the charge of, the oxidation number of our anion times the number of our anion plus the oxidation number of hydrogen times the number of hydrogen atoms minus the total charge, which is -0, divided by the number of sulfur atoms, which is 1. And that in turn gives us an oxidation number of sulfur. One moment. And that in turn gives us an oxidation number of sulfur equal to +6. Do these examples make sense so far? Any questions so far? Now, hydrogen, and you'll notice in the name, of these next few compounds, hydrogen can also adopt a -1 oxidation number when it's combined with metals, which are less electronegative atoms. We call these molecules hydrides because hydride is noted as H-. So let's assign some oxidation numbers. So sodium's oxidation number is +1 in this case, and as a result, hydrogen's oxidation number is -1. Hydrogen and calcium hydride adopts a -1 oxidation number. So what is the oxidation number of calcium, which is the less electronegative atom? What is the oxidation number of calcium? +2. Yep. Just to showcase that, just like if we're figuring out the charge of calcium, we take our subscripts and we reverse cross our subscripts to get our theoretical charges, which gives us calcium 2+ and H-. Okay, so continuing on with this idea, aluminum hydride, hydrogen has a -1 oxidation number. Aluminum, as a result, has what oxidation number? What's the oxidation number of aluminum in aluminum hydride?
+3.
+3, yep, exactly right. Okay, so let's look at another set of rules here. Halides or halogens, which are your group 7A elements, usually have an oxidation number of -1, except when paired with oxygen. Okay, if they're paired with oxygen, your halides have a positive oxidation number. So for example, in calcium fluoride, fluorine is more electronegative, so it has the negative oxidation number, and halogens prefer to have an oxidation number and a charge of -1. As a result, calcium has an oxidation number of +2. Okay, so now that we have that assigned, let's look at an example where we have our halogen bonded to oxygen. So in this case, oxygen is our more electronegative element, so it adopts its preferred oxidation number of -2. My question to all of you is, what is the oxidation number of chlorine then, if oxygen prefers an oxidation number of -2? What is the oxidation number of chlorine? What's the oxidation number of our least electronegative atom?
+1.
+1, yep. Just like, for example, if we were looking at sodium oxide, Na2O, sodium would have a +1 oxidation number and oxygen would have a -2. Okay, in dichlorine dioxide, oxygen adopts a -2 oxidation number. So what is the oxidation number of chlorine in this case? What is the oxidation number of chlorine? +2. Yep, exactly right. We're just crossing the subscripts into the oxidation number values. Perfect, perfect. So let's keep going now. So the oxidation number of oxygen and other group 6A elements is -2. But remember, the oxidation number assignments are based on electronegativity. So for example, in carbon monoxide, oxygen prefers an oxidation number of -2. So what is the oxidation number of carbon as a result? What is the oxidation number of carbon as a result? And don't be shy to share your responses in the chat or verbally. What's the oxidation number of carbon? +2, yep. Okay, perfect. So let's look at sulfur dioxide. In this case, oxygen is more electronegative. So we have an oxidation number of -2. So what would the oxidation number of sulfur be as a result? If the total oxidation number matches the total charge of 0, what is the oxidation number of sulfur?
+2.
So that's very close. So looking at this first and foremost, if we reverse cross our charges, that gives us an oxidation number of +2 for sulfur and -1 for oxygen. However, we always have to make sure that our oxidation numbers, especially for oxygen in particular, matches the oxidation number preferences. So we multiply each of our oxidation numbers by 2, and that gives us an oxidation number of -2 for oxygen and +4 for sulfur. Does that make sense? Any questions on this idea? Let's do another example just to make sure we understand this concept. So oxygen has a -2 oxidation number in sulfur trioxide. So what is the oxidation number of sulfur then? +6, exactly right. Okay, now there are a few exceptions. So oxygen has a -1 oxidation number in peroxides, where a peroxide is O2 2-. So for example, in hydrogen peroxide, each of the hydrogens prefer to have an oxidation number of +1. Oxygen in this case has an oxidation number of -1. Okay, in calcium oxide, oxygen has a -1 oxidation number. Calcium has a +2. Any questions? So continuing on, there's one other exception. Oxygen has an oxidation state of -1/2 in what are known as superoxides, where oxygen is written as O2-. So in this case, for example, sodium superoxide, sodium has a +1 oxidation number, oxygen has a -1/2 oxidation number. Okay, so let's keep going now. And let's talk about some additional rules for assigning oxidation numbers. And these are the central rules that you'll be using. So, first and foremost, the oxidation number of all atoms adds up to the charge of the molecule or ion. So your goal first is to identify the charge of the molecule in each component ion. And you're going to assign oxidation numbers to as many atoms as possible. Finally, you're going to solve for the oxidation numbers of the elements you did not assign. In other words, you can treat the compound like it's an ionic compound and assign theoretical charges using charge rules. Or you can use the following equation. We have a nice little summary table that captures many of the rules that we discussed in this earlier primer. So let's now try to apply what we've learned to assign the oxidation numbers to each atom in the following compounds. So calcium hydride. So hydrogen is more electronegative since it's bonded to a metal. So it'll prefer to adopt a -1 oxidation number. And calcium prefers to adopt a +2 oxidation number. Oops, one moment. Okay, let's look at oxygen difluoride. Fluorine is more electronegative, so fluorine will adopt a -1 oxidation number. Oxygen, in turn, is required to adopt, strangely enough, a +2 oxidation number. So, continuing on with this problem-solving session, looking at permanganate, MnO4. So let's first assign as many oxidation numbers as possible. So we know that oxygen overwhelmingly prefers to adopt a -2 oxidation number, especially because it's bonded to a less electronegative metal. So then we can now solve for the oxidation number of manganese by taking our oxidation number of oxygen times the number of oxygen atoms minus the total charge, which is -1, over the number of manganese atoms, which in turn gives us an oxidation number of +7. Do these examples make sense so far? Do these examples make sense so far?
I was wondering why you couldn't just do the switch.
For the bottom example?
Yeah.
It's because our total charge is not 0. If our total charge is not 0, so the total charge does not equal 0, then you can't just swap the charges because you have to account for this total charge when you're figuring out the charge of your cation. Does that make sense?
Yes.
Yeah, the equation works best for when the total charge is non-zero because you have to account for the total charge of your molecule. So the equation simply says if I add up, so what the equation is doing is if I add up all of the oxidation numbers of all of my atoms, so for example, the oxidation number of manganese times the number of manganese plus the oxidation number of oxygen times the number of oxygen, that in turn gives us our total charge. So what we're doing is we're solving this equation for the oxidation number of manganese. And this is just based on the idea that the total charge is the sum of all of our oxidation numbers. Does that make sense to everyone? Oxygen prefers to adopt a charge of -2, and it prefers to adopt an oxidation number of -2 overwhelmingly. Yep, and you multiply by 4 because we have 4 oxygen atoms. No, so this -1 is our total charge. And we're essentially solving this equation for the oxidation number of manganese by moving all of our terms to the right-hand side. Does that make sense? Yep. We're dividing by 1 because there's 1 manganese atom. That's exactly right. Any other questions? So let's test our understanding of the material and let's try to assign oxidation numbers to each atom in the following compounds. So don't be shy to Message me your proposed oxidation number assignments for each atom in each of these 3 compounds. And then we'll come together to discuss in about 5 to 6 minutes. So make sure you're comfortable calculating oxidation numbers for each atom in a series of compounds, because we'll use our oxidation number assignments later on to balance redox reactions. And we'll discuss this example in about 5 to 6 minutes. And don't be shy to propose your oxidation numbers for each atom. And just remember, the most electronegative atom gets a negative oxidation number, while the least electronegative atoms will typically have positive oxidation numbers. So for this response in the chat, the magnitude is correct, but make sure you're accounting for the fact that I want the oxidation number of an individual atom first and foremost, and that you need to account for the fact that your less electronegative atom will have a positive oxidation number. And for the response I received in the chat, just make sure you're accounting for the fact that oxygen typically has an oxidation number of -2 rather than -1. And that should fix the calculation. Don't be shy to message me with any questions or any proposed responses, and I'd be happy to provide feedback. And don't be shy to message me with your proposed responses, and we'll discuss in about another 3 to 4 minutes. I'd like to see a few responses in the chat, just so that way I know that everyone's comfortable assigning oxidation numbers. And we'll discuss this example in another 2 to 3 minutes. Don't be shy to propose in the chat or verbally your proposed oxidation numbers for each atom in any of the following compounds. And if there are any questions on this example, don't be shy to ask. Okay, so let's discuss this example. So in dichromate, so first and foremost, in Cr2O7 2-, we know that oxygen has a -2 oxidation number. So then we can now solve for the oxidation number of chromium by taking the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of chromium atoms, absolute value. That in turn gives us the oxidation number of chromium as +6. Does this example make sense so far? So let's look at the next example, which is potassium perchlorate. So let's try to get the easy things out of the way first. We know that potassium prefers an oxidation number of +1. Oxygen prefers an oxidation number of -2. So then, solving for the oxidation number of chlorine, we have -2 times 4. Okay. Plus the oxidation number of potassium times the number of potassium atoms minus the total charge of 0 over the number of chlorine atoms. And that in turn gives us an oxidation number of chlorine of +7. Any questions on these examples? Any questions on these examples so far? Any questions? So let's look at the last problem now. So in carbonic acid, so H2CO3, we know that the oxidation number of hydrogen is +1. Oxygen is -2. Okay, so then we can solve for the oxidation number of carbon by taking the oxidation number of oxygen times the number of oxygen atoms plus the oxidation of number of hydrogen times the number of hydrogen atoms minus the total charge over the number of carbon atoms. And that in turn gives us an oxidation number of carbon of +4. Do these examples make sense so far? Any questions on these examples? If not, let's continue on. And let's do another set of oxidation number questions. So we're asked to assign oxidation numbers to each atom in the following compounds. So in carbon dioxide, I know that oxygen has an oxidation number of -2. So then, as a result, if I cross my subscripts into the oxidation numbers, I get carbon 2+ and oxygen minus. Oxygen overwhelmingly prefers to have a -2 oxidation number. So we multiply each of our oxidation numbers by 2 to give us carbon with an oxidation number of +4 and oxygen with the oxidation number of -2. Now looking at chromate, so CrO4 2-, we know that oxygen overwhelmingly has a -2 oxidation number. So then we can now solve for the oxidation number of chromium. And the way that we do that, to solve for the oxidation number of chromium, we're going to take the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of chromium atoms. And that in turn gives us the oxidation number of chromium of +6. Does this make sense to everyone so far?
When you say total charge, you mean like the total charge of the oxygen?
No, the total charge of the molecule, which is -2.
Oh, okay. Yes.
Does that make sense?
Yes, thank you.
Perfect. So continuing on with this idea, looking at S2O3 or thiosulfate, first and foremost, let's get the easy assignments out of the way. And we know that oxygen overwhelmingly adopts a -2 oxidation number. So just to show the equation before we've rearranged it, we know that the total charge, which is -2, is equal to the oxidation number of sulfur times 2 sulfur atoms plus the oxidation number of oxygen times 3 oxygen atoms. So solving for the oxidation number of sulfur, we have the total charge minus -2 times 3 over 2. And that in turn gives us an oxidation number for sulfur of 2. Okay, so our oxidation number for sulfur is +2. Any questions on this example? Is everyone feeling a little more comfortable? Does everyone understand what the equation represents? Okay, perfect. So let's look at an example. If you're taking organic, assigning these oxidation numbers are going to be particularly important. So in CH4 methane, my question to all of you is our oxidation number for hydrogen in this compound going to be positive or negative? Is our oxidation number for hydrogen going to be positive or negative?
Negative?
So to rephrase, what's more electronegative, carbon or hydrogen? Which atom is more electronegative, carbon or hydrogen? Which atom is farthest to the right and closest to fluorine on the periodic table? Carbon, yep. So carbon is more electronegative, and as a result, because carbon is more electronegative, it will adopt a positive, because it's more electronegative, it will adopt a negative oxidation number, and so hydrogen will adopt a positive oxidation number, because hydrogen, by extension, is less electronegative than carbon. So then we can solve for the oxidation number of hydrogen by reverse crossing our charges, and that gives us an oxidation number of hydrogen of +1 and carbon of -4. Does this make sense to everyone so far? So in general, hydrogen will have a positive oxidation number unless it's bonded to a metal. That's the only exception for hydrogen. So let's look at another example, aluminum chloride. So if we reverse cross our charges, that gives us aluminum with an oxidation number of +3, chlorine with an oxidation number of -1, and those assignments seem perfectly reasonable. Okay, so let's look at another example. In this case, we have CHCl3, otherwise known as chloroform. So let's assign all of the easy oxidation numbers first. So hydrogen, what is the oxidation number of hydrogen in this case? +1, yep. Exactly right. And what is the oxidation number of chlorine? What is the oxidation number of chlorine? Chlorine in compounds. So pure elemental chlorine, yes, it has an oxidation number of 0, but in compounds, to rephrase this another way, in most compounds, what would the charge of chlorine be? What would the charge of chlorine be?
-1.
-1, yep. So the oxidation number of chlorine and other halogens is overwhelmingly -1. So now we can solve for the oxidation number of carbon. So we know that the total charge, which is 0, is equal to the oxidation number of carbon times the number of carbon atoms plus the oxidation number of hydrogen, which in this case is +1, times the number of hydrogen atoms plus the oxidation number of chlorine, which is -1, times the number of chlorine atoms. So that in turn gives us our oxidation number of carbon is equal to 3 - 1 over 1, which gives us an oxidation number of +2. Oh, actually, sorry, one moment. Three - 1 + 2. Yep, exactly right. So carbon has an oxidation number of +2 in this compound. Does that make sense to everyone so far? Any questions on these examples? Okay, so let's try to apply what we've learned. And now that we went through a series of oxidation number assignments, let's talk a little bit about oxidation and reduction half reactions. Sorry, the way that we got the 3 from is we have 3 chlorine atoms, and each of the chlorine atoms have an oxidation number of -1. Perfect. So let's now look at oxidation and reduction half reactions. So a half reaction is a balanced ionic equation that indicates the electrons gained or lost by the oxidizing agent or reducing agent. Now, the reducing agent is defined as the species that donates electrons. The reducing agent is oxidized as its oxidation number becomes larger and more positive. An oxidation half reaction is a half reaction where we lose electrons. So the electrons are on the product side. So another example of an oxidation reaction would be if we went from chloride to chlorine plus 2 electrons. One thing I want you to pay attention to is if we look at the oxidation numbers, from sodium to sodium plus, we're going from 0 to +1. From chloride to chlorine, we're going from -1 to 0. So in both cases, our oxidation number is becoming more positive. Does that make sense? Okay, so the reactant that loses electrons is said to become oxidized, and it is the reducing agent. So the reducing agent gives electrons, loses electrons, and as a result, it is oxidized. So to give electrons is to lose electrons. Now, what's really important to keep in mind is that the number of electrons lost is equal to the difference between the total product and total reactant oxidation numbers. So in this case, for example, when we go from sodium to sodium plus, we go for an oxidation number of 0 to +1. So we have a net difference of 1, and we have underwent this change in oxidation number 2 times, so that gives us 2 electrons lost. Does that make sense to everyone? Let's look at another case. So for bromine, we went from -1 to 0, so we have a difference of 1. We've underwent this process 2 times because we have 2 bromine atoms. So that in turn gives us 2 electrons lost. Is everyone feeling comfortable counting electrons? Do these rules make sense? Okay, so let's now talk about the other subclass of compound in oxidation and reduction half reactions, which are oxidizing agents. So oxidizing agents are the species that gains electrons. So the oxidizing agent is reduced as its oxidation number becomes smaller or more negative. So for example, we went from chlorine, which is 0, to chloride, which has an oxidation number of -1. So our oxidation number was reduced as we have gained electrons. So the reduction half reaction, is the half reaction where the reactant gains electrons. The electrons are on the reactant side. The reactant that gains electrons is said to be reduced, and we call this reactant the oxidizing agent. Again, the number of electrons gained is equal to the difference between the total reactant and product oxidation numbers. So in this case, if we go from +3 to 0, our difference, if we take the final minus initial, is equal to 3. So we have 3 electrons gained. Likewise, from chlorine to chloride, we went from 0 to -1. So our difference is 1 times 2, which gives us 2 electrons gained. So just as a summary to help you organize your ideas, the species that is reduced is known as the oxidizing agent. So the species gaining electrons is taking electrons. The species that is oxidized is known as the reducing agent. The species that is losing electrons is donating electrons. Okay, so let's look at the following example. And our goal is to identify the half reaction as an oxidation or a reduction half reaction. We're then going to indicate the number of electrons gained or lost and assign each species as the oxidizing or the reducing agent. So looking at our first example, so aluminum, we went from 0 to +3. So then we are increasing in oxidation number, so we are losing electrons. And if we're losing electrons, we're looking at an oxidation half reaction. And this aluminum, as a result, if it's losing electrons, it's donating electrons, and we'd say aluminum is a reducing agent. So we've lost 3 electrons. Does this example make sense so far? If our oxidation number is increasing, it's getting more positive, larger and more positive, we are losing electrons, our species is being oxidized, so it's a hot oxidation half reaction, and our reactant is acting as a reducing agent. It's donating electrons. Okay, so let's look at the next example. So we have S2O3. So we know that the oxidation number of oxygen is -2. For sulfur, our oxidation number in this compound is +4. Let's look at S4O6. So the oxidation number of sulfur is equal to the number, is oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of sulfur atoms. So that in turn gives us 10/4, which turns into 5/2. Okay. So we went from +4 to +5/2. So in turn, we went from an oxidation number of 2 to an oxidation number of 2.5. Since our oxidation number is getting larger, we are losing electrons. And to figure out exactly how many electrons we've lost, we're going to take our difference, which is 2.5 minus 2. So we have our difference of 0.5 times the number of sulfur atoms, which is 4. So we have 2 electrons lost. So then this reaction, if we are losing electrons, we'd consider this an oxidation half reaction. And as a result, thiosulfate is known as a reducing agent because it is donating electrons. Does this example make sense? There's a logic of calculating the number of electrons gained and lost by looking at the difference in oxidation number for each atom and the number of atoms that were oxidized or reduced. That allows us to calculate the total number of electrons gained or lost. If your species is losing electrons, it's an oxidation half reaction, and we call our reactant a reducing agent. It's losing electrons, it's donating electrons. So let's test our understanding, just as I don't see any major questions. So I'd like you to look at the following 3 reactions, and I would like you, so for the following 3 reactions, I'd like you to calculate the number of electrons gained or lost. I'd like you to assign oxidation numbers to each atom. In terms of pages, this is 50, page 50. And this is the Chapter 7 notes, Part 3, which are on Canvas. And then once you've assigned your oxidation numbers and figured out whether you're gaining or losing electrons, I'd like you to calculate the number of electrons gained or lost and tell me, are these reactions oxidation or reduction half reactions? And is our reactant an oxidizing or reducing agent? So let's spend about 6 to 7 minutes on this example. And if you have any questions, don't be shy to ask or message me your proposed responses or questions in the chat, or you can submit your proposed responses verbally. And we'll discuss this example in about another 6 to 7 minutes. But don't be shy to message your proposed responses for any of these reactions, and I'd be happy to provide feedback. And the responses I see in the chat looks perfect so far. The response I see in the chat assigning these reactions as oxidation or reduction reactions, you have them exactly reversed. So remember, oxidation is losing electrons. Your oxidation number is becoming more negative, while reduction is gaining electrons. Your oxidation number so just to be 100% clear here, so for oxidation, you are losing electrons. You're losing electrons. So as a result, your oxidation number is becoming more positive. Your electrons are on the product side. For reduction, your oxidation number is becoming more negative as you're gaining electrons, and your electrons are on the reactant side. So let's keep working on this example, and we'll discuss in about another 5 minutes. And the responses I see in the chat so far look quite good. Let's keep working through this example, and we'll discuss in about another 3.5 to 4 minutes. And don't be shy to message your proposed responses for each of these reactions in the chat. So once you've assigned whether the reaction is an oxidation or reduction half reaction, I'd like you to identify the number of electrons gained or lost in each reaction. And we'll discuss this example in another 2 minutes. And for the response I see in the chat, make sure you account for the fact that multiple atoms could be undergoing changes in oxidation number. Okay, so let's discuss this example. So first and foremost, for the following example with copper, we're going from an oxidation number of +2 to 0. Okay, so our difference is going to be 2 electrons, and we have 1 copper atom undergoing the change. So we have 2 electrons total. Our oxidation number is decreasing, so we're gaining electrons. So if we're gaining, let me use the right color for that. So we have gaining electrons. So this is a reduction half reaction. Okay, let's look at another example for iodide to iodine. We're going from an oxidation number of -1 to 0. So our difference is 1 electron, and we have 2 atoms undergoing that change. So then we have 2 electrons, and as our oxidation number is becoming more positive, we are losing electrons. So as we are losing electrons, we call this an oxidation half reaction. Looking at the last example, we go from +1 to 0. So our difference is 1 electron, and we have 2 hydrogen atoms. So we have 2 electrons. Our oxidation number is decreasing and becoming more negative. So we're gaining electrons. And as we are gaining electrons, we call this a reduction half reaction. So gaining electrons, this would be a reduction half reaction. Does this example make sense to everyone so far? Any questions so far?
When you say difference, is it because you're subtracting those two numbers?
Yes. Yep. I'm taking the difference between my final and initial oxidation number.
Thank you.
Yep. And the difference in oxidation number determines the number of electrons gained or lost for an individual atom. And then you have to scale that by multiplying by the number of atoms that changed in oxidation number. And since we have, for example, 2 in this iodide example, we have to multiply our change by 2, since 2 iodines are losing electrons. Does that make sense? Okay, so let's keep going now. And this time we're going to do a little bit more involved examples. These are closer to the types of redox reactions that you typically encounter. So we're asked to assign the half reaction as oxidation or reduction, and then we're going to calculate the electrons gained or lost. Okay, so let's assign oxidation numbers. So iodide, it's -1. In iodate, which is IO3-, the oxidation number of iodine is equal to the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of iodine atoms. And that in turn, if we punch this into our calculator, gives us an oxidation number of iodine of +5. Okay. So we went from -1 to +5. So our delta is 5 minus -1. So our delta is 6 electrons times 1 iodine. So we have 6 electrons. And as our oxidation number is increasing, we are losing electrons. And if we are losing electrons, that in turn means that we have an oxidation reaction. Further, as a result of this, we'd say that iodide would be a reducing agent. The species that loses electrons is giving electrons, and we call that the reducing agent. Let's look at another example. So in chromate, so CrO4 2-, the oxidation number of chromium is going to be equal to the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of chromium atoms, which gives us an oxidation number of +6. So we're going from +6 to +3. So our difference is equal to 6 minus, well, our difference is equal to 3 minus 6, which is 3 electrons. We have 1 chromium atom. So we have 3 electrons. And since our oxidation number is decreasing, we have 3 electrons gained. So this is a reduction half reaction. And as a result, chromate is an oxidizing agent. So we've gained 3 electrons. Does this idea make sense to everyone? This idea of counting electrons, assigning oxidation numbers, and determining whether it's an oxidation or reduction half reaction by looking at whether your oxidation number is increasing or decreasing. Any questions on this example? The only thing that's new in this example is you have to be a little more careful about how you calculate your oxidation numbers. Okay, so let's look at the following example. So I'd like you to assign oxidation numbers, determine the electrons gained or lost in the reaction, and then I'd like you to tell me whether it's an oxidation or reduction half reaction. And we'll discuss this example in about 5 minutes. But don't be shy to submit your responses in the chat or verbally, or any questions that you have in the chat or verbally in the meantime. And for the response that I see in the chat, you're correct in your assignment of an oxidation versus reduction half reaction, but I would double check your oxidation number assignment to make sure you've counted the number of electrons gained or lost correctly. And we'll discuss in another 4 minutes. But don't be shy to message me your proposed responses or any questions that you have in the meantime. Yep, and the response I see in the chat looks perfect. One moment, let me just check. And the response I see in the chat for the second question also looks perfect. Yep, looks fine so far. And we'll discuss this example in another 2 to 3 minutes. And we'll discuss this example in another minute to a minute and a half. Okay, so let's discuss this example. So first and foremost, in permanganate, the oxidation number of manganese, let me switch pen colors for that. So the oxidation number of manganese is equal to the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of manganese atoms, which gives us an oxidation number of +7. Okay, in manganese 2 plus, it's +2. So our difference is 2 minus 7. So we have 5 electrons times 1 manganese atom, which gives us 5 electrons total. One moment, allow me 1 second just to reset OneNote. Okay, so our oxidation number of manganese went from +7 to +2. So our difference, our amount of electrons gained in this process is 2 minus 7, which gives us 5 electrons times 1 manganese atom. That gives us 5 electrons gained total. Okay, as we are gaining electrons, we would call this, and so if we're gaining electrons, we call this a reduction half reaction. And this manganese species would be an oxidizing agent. So we put our 5 electrons on the left-hand side. Does this first example make sense to everyone? Does this first example make sense? Okay, so let's keep going. So we have nitrogen monoxide. So we'd assign the oxidation number of nitrogen as +2 in this case. In nitrate, the oxidation number of nitrogen is equal to the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of nitrogen atoms, which in turn gives us an oxidation number of +5. Okay, as our oxidation number is increasing in magnitude, 5 minus 2 gives us 3 electrons times 1 nitrogen atom. So we have 3 electrons lost. So we are losing electrons. Ergo, this is an oxidation half reaction, and nitrogen monoxide is going to be a reducing agent because it's donating electrons. Do these examples make sense so far to everyone? Any questions so far on these examples?
So is it considered losing because you went from the 5 to the 3?
So it's considered we're losing electrons because our oxidation number went from +2 to 5. Our oxidation number is becoming more positive, and as a result, that means we've lost electrons.
And you can't just see that from looking at the problem?
What do you mean?
I guess because, or actually, no, I'm starting to see it now. Never mind, that makes sense.
Are you sure?
Yes, actually, I didn't realize the word right here real quick.
Another way of looking at it is that if your difference of final minus initial is positive, that implies you've lost electrons. If the difference is negative, that implies you've gained electrons.
Okay, thank you.
Yeah. Mm-hmm. Okay, so we're developing this skill of counting electrons. So let's talk a little bit about what makes a redox reaction balanced, because redox reactions are balanced using a different set of rules than normal chemical reactions. So first, electrons are conserved in redox reactions. The number of electrons that are lost by the reducing agent must match the number of electrons gained by the oxidizing agent. Now, when you combine your half reactions, they should match the overall balanced chemical equation. So we should clearly see equal numbers of electrons in the reactant and product side of a balanced redox reaction. So for example, if we have our oxidation and reduction half reaction, so we have 2 electrons on each side, our 2 electrons cancel. Similarly, if you're combining 2 redox reactions together, identical species on the reactant product side will cancel out when you combine your chemical equations. So for example, if you combine these 2 equations, your 10 electrons cancel. You can also cancel 10 H plus from each side and 5 water from each side. And that in turn gives us the following balanced chemical equation, where we've just canceled out common numbers of shared ions on each side of our equation, just like we did when we were writing net ionic equations. So this would be our final equation if we've canceled out all of the common species on each side. Does that make sense to everyone? That when you add your redox reactions together, the number of electrons should cancel, and you should cancel any identical species with the same formula on each side. Note, you're not just getting rid of everything. You're only getting rid of the same number of that species on each side. So if we have 10 H plus on this side and 16 H plus on the left, we can get rid of 10 from each side. Does this idea make sense?
Wait, so for the top one, how did you get 3 when you cross out 8?
Because we have 5 water on the left and 8 minus 5 gives us 3. While 5 minus 5 gives us 0. Since we have water on each side, if we have 8 on the right and 5 on the left, we can cancel 5 from each side. So 8 minus 5 would give us 3.
Oh, so you're doing them together.
Yep.
Oh,
Just like for H plus, we canceled 10 from each side. 10 minus 10 gives us 0. And 16 minus 10 would give us 6. Does that make sense?
yes.
Perfect. Okay, so let's do a guided example where we assign oxidation numbers. We identify the oxidizing and reducing agent. We write the half reactions, and then we show that electrons are conserved. Okay, so first things first, we assign oxidation numbers. Manganese solid is 0. Cobalt in cobalt nitrate is going to be +2. Manganese in manganese nitrate is +2. Cobalt solid is 0. Okay, so manganese, we went from manganese solid to manganese 2+ aqueous. Okay, so if we went from 0 all the way to +2, we're losing electrons. So we put them on the product side. So our difference is 2 minus 0, which is 2 electrons times 1, which is 2 electrons lost. Okay, so since we're losing electrons, we classify this first reaction as the oxidation half reaction. Now looking at cobalt, we went from cobalt 2+ aqueous to cobalt solid. So we went from an oxidation number of +2 to 0. So our difference, 0 minus 2 is -2 times 1. So we have 2 electrons gained. As we have 2 electrons gained, we'd call this reaction the reduction half reaction. So now when we add our equations together, we get magnesium solid leads to magnesium 2+ aqueous plus 2 electrons. And then we have 2 electrons plus cobalt 2+ aqueous leads to cobalt solid. And if we add these equations together, the 2 electrons cancel and we get magnesium solid plus cobalt 2+ aqueous leads to magnesium 2+ aqueous plus cobalt solid. And this equation serves as our net ionic equation in most cases. Does this example make sense to everyone so far? Does this idea make sense to everyone so far? Okay, so let's apply what we've learned to the following example. So I'd like you to look at the following reaction. I'd like you to assign oxidation numbers, identify the oxidizing and reducing agent, and write the half reactions, and then show that electrons are conserved. So we'll spend about 4 to 5 minutes on this example. And don't be shy to message any questions or your proposed responses in the chat. And don't be shy to message me your proposed responses in the chat. And thankfully, this equation is already balanced, and we'll talk in later parts of this chapter about how to balance this chapter and how to balance redox equations. And we'll discuss this example in another 2 to 3 minutes. Okay, so let's discuss this example. So first and foremost, we're going to assign oxidation numbers. So aluminum has a total charge of 0, oxidation number of 0. So copper and copper chloride has an oxidation number of +2. Aluminum and aluminum chloride has an oxidation number of +3. And copper, as a pure metal, has an oxidation number of 0. So now let's look at aluminum. So for aluminum, we went from 2 aluminum to 2 aluminum 3+. We went from an oxidation number of 0 to +3. So our difference in oxidation number is 3 minus 0. So we have 3 electrons and we have 2 aluminum atoms. So that gives us 6 electrons total. So in turn, we lost 6 electrons. So this would be our oxidation half reaction. Let's look at our next example. So for copper, we go from copper 2+ to copper 0. So in turn, we went from +2 to 0. So our difference is 0 minus 2, which is -2. Now noting and looking at the number of copper atoms in our equation, we have 3 copper 2+ going to 3 copper. And that gives us ×3. So we have 6 electrons. But in this case, we have 6 electrons gained. So we have +6 electrons. So this is our reduction half reaction. If we add our two equations together, so we have 2 aluminum plus 3 copper 2+ leads to 2. Let me add them together step by step. So adding our top equation to our bottom equation, we have the same number of electrons on each side, so that cancels to give us 2 aluminum plus 3 copper 2+ leads to 2 aluminum 3+ plus 3 copper solid. There we go. And interestingly, when we add our equations together, we get the net ionic equation for this reaction. Any questions on this example? Any questions on this example? Any questions? Okay, so let's now look at a slightly more involved example. So I'd like you to assign the oxidation numbers for the following compounds in this redox reaction. I'd like you to identify the oxidizing and reducing agent. And then I'd like you to show that electrons are conserved when you add your oxidation and reduction half reactions together. So let's take a few minutes to work through this example, and we'll discuss in about 5 minutes. And don't be shy to message me your proposed half reactions in the chat, ask any questions in the chat, or ask any questions verbally. And if you have any questions at all working through these problems, don't be shy to ask. I'd like to see a few proposed half reactions in the chat, just so we can discuss. And we'll discuss this example in another 3 to 4 minutes. And don't be shy to share your proposed responses in the chat, or if you need more time on these problems, don't be shy to let me know. And we'll discuss this example in about another 2 minutes. And if you have any questions working through this problem, the responses I see in the chat look good so far. Let's try to get a few more responses in the chat. Okay, so let's discuss this example. So first and foremost, let's assign oxidation numbers. So in thiosulfate, so for sulfur, we have the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of sulfur atoms. That gives us a sulfur oxidation number of +2. In hypochlorite, chlorine has an oxidation number of -2 for oxygen minus the total charge of -1 over the number of chlorines, which gives us an oxidation number of +1 for chlorine. In S4O6 for sulfur, we have -2 times 6 minus the total charge of -2 over the number of sulfur atoms. So for sulfur, we get an oxidation number of 5/2. Yes, there is 4 atom. In which calculation? In which when you say 4 atoms of sulfur, and this is really important. You don't have to worry about the coefficients when you think about oxidation numbers. You worry about the coefficients when you think about the total number of electrons gained or lost. Does that make sense? Perfect. So even though it may seem a bit odd that we have a fraction for our oxidation number, that is one quirk of oxidation numbers, in that sometimes the electron density can be distributed across multiple atoms in your compound. So we end up with these fractional oxidation numbers. And we'll see partially why that is when we look at chemical bonding. Okay, so after a few exciting oxidation number examples, chlorine is easy. It's just -1. Okay, so let's start off by looking at our oxidation half reaction. So in our oxidation half reaction, we're losing electrons. And what species is found in our oxidation half reaction? What atom is being oxidized? What atom is losing electrons going up in oxidation number? What atom is being oxidized? Sulfur or chlorine? Which one's being oxidized? Sulfur or chlorine? Which species is having an oxidation number that's
Sulfur.
becoming more positive? What was that?
Sulfur.
Sulfur, yep. For sulfur, we're going from S2O3 2 minus. So we went from +2 to S4O6 2 minus, which is +2.5. So our difference is equal to 2.5 minus 2, which is 0.5. So 0.5 electrons times 4 sulfur atoms gives us 2 electrons lost. And since we're losing electrons, our electrons go on the product side. Does that make sense to everyone? Does that make sense to everyone? Any questions on this example? So let's look at our reduction half reaction. The reason why I multiplied by 4, this is the number of sulfur atoms. So this delta is the change. This is electrons per every 1 sulfur atom in this reaction. And we multiplied by 4 because 4 sulfur atoms are undergoing a change in oxidation number. Does that make sense? Perfect. So for our reduction half reaction, we're going from hypochlorite and water to chloride and 2 molecules of hydroxide. So looking at our oxidation numbers, we went from an oxidation number of +1 to -1 for chlorine. So then the delta would be -1, -1, which is 2 electrons. 2 electrons times 1 gives us 2 electrons. And this is 2 electrons gained. So we have 2 electrons gained. So we place our number of electrons on the left-hand side. Does that make sense to everyone so far? Now, just to showcase that this reaction is in fact balanced, so we have thiosulfate, the thiosulfate dimer, 2 electrons lost, 2 electrons gained, plus water plus hypochlorite leads to chloride and 2 hydroxide. Our electrons cancel and we're left with the following complete balanced chemical equation. As follows. So this redox reaction is balanced because our number of electrons in the reactant and product side are equal and they cancel out. Does that make sense to everyone so far? Any questions on this example? So, as we likely won't, we're likely going to have to finish these next examples in our supplemental lecture later today. What we're going to do is we're going to take a quick break and then we'll resume for laboratory at 12:40.